We're good. Okay. Cool. Hello. Oh, you can hear me. Great. Yeah, let's get started. Welcome to Lecture 7. It's our second to last one, but our last one with any before the review, so hope you're excited for this last bit of content. This is too loud. It's much too loud. Okay, cool. So yeah, Lecture 7. Here's some announcements. There's the live lecture thread up if you want to ask any questions that we can't get to during lecture. In addition, if you are all aware, there's a Project 3 Bear Maps. It's due on Friday, so that's 2 days from now. The auto graders for both the normal project and the extra credit are available on Gradescope. And then we're going to have a project workday on Friday. So if you don't quite have it done, then there will be time on Friday. In addition, we will have our last quiz and our self-reflection due on Friday. What that means is that although it's a project work day and you technically don't have to come in for that, you should still probably come in for your quiz because that's part of your grade. So yeah, make sure you come in for the quiz this Friday. Okay, any other announcements before we keep going? I think that's it for now. Okay, so if you've noticed, recently we've been talking about sorting. That was yesterday's lab. And so we're just going to start with like a quick reminder on like some of the stuff we learned yesterday before we hop into other types of sorting for tomorrow's lab. So here are the sorts that we've learned so far. We saw this in the lab on the worksheet. And so like these are things we know, right? We're all familiar with like how these work, hopefully, and if not, we have some demos here that you can check out. So if you're thinking, oh, I kind of forgot how heap sort works, you can always click on the demo in these slides and it'll take you to an example of how heap sort works. You can always ask on Piazza. Anything there will get you sorted out. Cool. So here we have our different sorts, and then we've kind of expanded on that table we learned in the worksheet a little more. So for each of our sorts, we think about what memory we'll be using, what our best case runtime is, our worst case, any notes we have on it, like things that make it interesting, and then whether it's usually stable. So we have selection, where we just go through, we select the minimum, we place it at the beginning. We do that a bunch of times. We don't have to use any additional like memory besides some constant amount to move stuff around. It's always going to run in n squared, and it's pretty much not stable given the algorithm we learned. We've got insertion, where as we scoot up through our list, we take each element and we insert it back into the sorted part of our array at the position it should be through a series of swaps. So in the best case, it's already sorted, we're good. In the worst case, it's flipped order. It still takes n squared, right? So insertion's good if we're almost sorted, right? And then it's generally stable. Then there's heap sort, where it's not going to take much more memory because we can do heap sort in place. If all the elements are the same, this just takes n time. If they're not all the same, this can take n log n time. And then notes, things that you don't have to know right now, it's got bad caching, which basically means when you're moving all this stuff around in heap sort because you're pulling from like the end and the beginning, you're doing a lot of movement, it basically like is bad for your computer's memory because it moves stuff around. You'll learn that when you take 61C, but that's just something to note where you think, oh, worst case runtime is n log n, but due to things that we don't quite know yet, we might not actually want to use heap sort. And then again, heap sort's usually not stable. Then we learned merge sort and quick sort, and this is the one where we're kind of thinking like, okay, like merge sort, it's always like n log n, we're gonna do great. It's gotta be better than quick sort. Then like as we learn more, like we might find that quick sort actually runs faster. These are our two kind of competitors for our fastest sort. But what we know is that merge sort's gonna have to use n memory as it recreates that array as it goes down. And then it's always gonna be an n log n asymptotically. And so what's important is it's gonna be our fastest stable sort because it's always gonna keep things stable as we go. But quick sort in practice is actually gonna usually be faster than merge sort, because although its worst case is n squared and like its best case can be n, it's usually going to be about n log n, but it's going to be our fastest sort, not always stable. We can make it stable though. Yeah, Kristen? Yeah, so what's important so Christine was bringing up the idea that we can make quicksort stable, but what'll happen is if we do some of our that's at the end of the lectures that I was going to touch on, is we can make all these sorts stable if we're careful, but what that'll do is it'll cost us efficiency in our memory and our runtime. So if we want to make quicksort stable, we can do that, but it can make it slower than merge sort for certain examples. Cool. Okay, any other questions on, so yeah, this stability is kind of like no asterisk. You can always make these stable with some other modifications. Matt brought up the other day that if we always add in an extra piece of information about each element, about its original index, we can change the way that we sort things and they'll always be stable no matter what sort we use. Anyway, any questions on this so far? Yeah? Yeah, so I actually just talked about that and how depending on like which type of quicksort you use, it will or won't be stable. If we want it to definitely be faster than merge sort, you won't be able to use your stability version of quicksort. But if you if you want it to be faster, it won't necessarily be stable. But the version we used will be stable because it just will happen to be slower than merge sort at times, right? So it's all kind of no asterisk. I was going to get to that at the end of the lecture, but I guess I should have put it at the front. Any other questions for now? Yeah. Yeah, so based on like if you're doing it in a stable way or a non-stable way, and like it's basically a bunch of like empirical stuff, not asymptotic stuff. But if you actually like check, because basically it has to do with the memory and like how many like comparisons you're doing and like what the actual inputs are. There are cases where one will outperform the other based on which type of quicksort you're using. Cool. Okay, moving on. So now we're talking about, so of all these sorts that we found the best like worst case time we can get is n log n, right? In our best sorts, like quicksort and merge sort and like heap sort, in the worst case they're going to be n log n, right? So we're thinking like, okay, like how can we try to improve that, right? How can we get to a sort where its worst case is better than n log n? And so far we've got this idea that like, okay, it looks like we've kind of hit a wall with n log n. So what we've been doing so far is as we sort stuff, we do it by comparing elements, right? And so we found that our fastest worst case runtime is n log n. And then what we can do is there's actually some math out there that'll prove that the lowest worst case bound for comparison-based sorts is n log n. So we can't actually do any better than that, right? So in the worst case, we'll always like run right up against that n log n bound. But this is for comparison-based sorts. And the question is, what does it mean when I say this is for comparison-based sorts? What we're going to try to come up with is a way to beat this worst case runtime and be even faster than n log n. But how will we do that? We're going to try doing it by not ever making any comparisons between elements. So far we've thought like, oh, selections, I'll compare to find the minimum. And like insertion, I'll compare to see which swaps I should make. And merge, I'll compare to see which one should go first. We're going to try to do this without any comparisons and see if we can get faster. So here's an example that I borrowed from Josh Hugg. And basically, here's an idea called sleep sort. So we have an array of integers, and for each integer x in the array, we start a new program where it sleeps for however big that integer is, like doesn't do anything, and then at the end of that time, after it's waited for that many seconds, it's going to print out that number. And then we start them all at the same time, and then what's going to happen? Well, the runtime should theoretically just be n, because that's how many like times we're starting this program, and then whatever the max of all these integers is, right? Because we have to wait for that many seconds. Makes sense, right? So like boom, we've just sorted it in n time because we just wait, and then like if we have like all the integers from like 1 to like 100 and they're all in the random order, to sort them we just sleep for a certain amount for each integer, and then it'll print them out in order, and it'll print 1, 2, 3, 4, 5, and they'll come out printed in sorted order, right? Boom, we're done, sorting, solved. Well, it doesn't quite work like that because there's a bunch of other information that'll come up, and the idea that for your computer to actually know how to like run all these programs simultaneously, it's going to have to do its own sorting of all the like processes on your computer, which in itself will take longer than n time because it has to know which program to run at which time. So theoretically, if we had like a perfect computer that could run everything simultaneously, maybe this would work. But in practice, it's not really going to get us to where we want to be. And yeah, basically, someone posted this on 4chan, and they were like, look, I'm a genius, but we know, yeah, probably not. Okay, so here's another idea. Let's use this idea of counting stuff. So instead of like thinking like, okay, I want to like do this in terms of like time, let's try to do this in terms of like space. Like let's use the idea that like maybe I can just use a bunch of space instead of using a bunch of time to get my sorts done. So we'll say here are a bunch of like entries, right? And it's basically like a number to like uniquely identify an entry. It's going to be a name, a type of ice cream they like, and then stuff about bands. I don't know all these. I know like 2 of them. But yeah, so basically each of these is a full entry, and they're each identified uniquely by their integers. So we have the integers 0 to 11 up here, right? And each one represents an entry. And what we'll do is we'll create a new array, and then we'll take each item with some key, since it's 0 to 11. We're going to make an array of length 12, and then we're just going to copy each entry over to the array, and then maybe this will have it sorted. So what we'll do is we'll go here, we'll take the first thing, we'll say, okay, that's number 5. I'll copy it over into position 5. So far that should be sorted, right? Since we know it's 0 to 11 and it's all of those integers, this will be like at position 5 at the end, right? Since we're sorting based on the number. And then we go and we say, okay, this next one is 0, so we'll put it there. And we just go ahead and put everything into its index. And then, boom, we're sorted. Life's good, we're done, right? Sorting has been solved a second time in like 2 minutes. Okay, why might this not work? Like for every type of sort, or for every type of like input. What's something that could make this slow? If we don't have all the data to begin with, like it's not a complete list and we have to sort as we go. Yeah, that could be something. What's another thing that could make this not work? Yeah?
We wouldn't actually know like the index of where things go. Like we could guess and then like be wrong. There could be more elements before.
Well, why would we be wrong? We know that it's from 0 to 11 and we have all the ints.
Are you saying for like a general case what we don't know? 0 to 11?
Yeah, exactly. So that you're touching on it. So if a general case is happening, we don't know that we're having from some like number to another number with all the ints inclusive, right? What if we have duplicates? What if we have gaps? Stuff like that. Doesn't always work, right? So reasons like that are why this sort of thing might not work. So let's see what we can do to get better than that. So what we're going to do is, this was a good idea, right? Where we were like counting and saying, how many things do we have? Now we can start filling an array. So let's generalize it to this thing called Countersort, right? So what we did here is we basically said, all right, I took n things and I put it in n worst time because I just threw them into another array. What's important is like, did we ever compare any item to any other item? No, we just looked at like the indices that it should go at and we put it right there. There were no comparisons that we made between elements. So if we avoid making those comparisons, we can do this in n time. We don't have to like run into that n log n bound. But this is like a very, very, very simple case where we say keys are unique integers from 0 to n minus 1, right? There's no gaps, there's no duplicates, none of that. So if we have other cases where we have keys that aren't unique, keys that aren't consecutive, or keys that aren't even numbers, how do we put things into that array, right? So let's talk about it. So over here is an idea of like how counting sort, of this idea that we just tried, let's expand it, right? So let's say that we have an alphabet, right? Has anyone here played with like a deck of cards before? Got 2, 3 maybe? Okay, cards, they're like yay big. They've got different suits on them. There are 4, and then there's numbers. Okay, cool, now you know how to play cards. Okay, so basically there's 4 suits, so there's 4 categories of cards, right? And so there's clubs, spades, hearts, and diamonds, right? And let's say that those are the only 4 things that we're going to like think about. And we'll say, this is our entire alphabet, right? It's going to be these 4 suits, and it's going to be in that order. So clubs are less than spades, which are less than hearts, which are less than diamonds, right? Now, let's think about how we would sort all of these things here based on that. So we have a spade and Lauren as the first pair, and we have a heart and Delbert as the next pair. And we're going to go ahead and we're going to start sorting everything. So if we know that it's in this order, right, where all the clubs go first, then all the spades, then all the hearts, then all the diamonds, could we calculate what the index of the first heart would be? You can talk to your neighbor and see if you can come up with the index. I'll give you like 20 seconds. Okay, any ideas for where the first heart entry would fall in our final array, if we know that it's in this order? Like if we know that we go clubs, then spades, then hearts, then diamonds?
Index 5?
Why? Just cause? Well, that's a good guess, okay. So what we did is kind of look through and we said, okay, well, I mean like for me in my head I said, okay, well I know all the black colors come before, so I'm going to count out 1, 2, 3, 4, 5 of the black suits, and then I'll say, well, then the next one after the black suits is hearts. So, okay, the heart is going to come at 5, right? But how long did that take me? Well, all I have to do is start from the top and scan through and get a count for everything that is like a black suit, so I can scan through. Took me n time to get to the bottom, and then at the end I have the number 5, and I can say that's where the hearts begin, right? So that's what I did, and so not so bad, right? I just scanned through an n time, and now I know where each of them are going to begin. So this is the idea of like counting sort, right? If I wanted to know where the spades would begin, I would scan through which suits would I pick out if I wanted to find where the spades begin. What would I count? I heard someone say clubs, right? So we count the total of the things that came before, and then we know the index of where those things will start. Counting sort. Okay, so what we'll do is to go through this whole thing, or let's just go through a full demo of it, basically. But what we'll do is we'll count the number of occurrences of each item, and then as we iterate through the list, we use the count array to decide where we want to place everything, and then from there, we'll know like where things should start, and then we start placing things in. So here's a demo. It's going to happen. Go. Go. Okay. So, go. Go. Cool. Okay, counting sort. So this is what we're going to start with, right? And then what we're going to do is we're going to say, okay, so first we'll scan through in linear time and we'll get our counts, right? And we say, how many clubs are there? There's 3. How many spades are there? There's 2. How many hearts are there? There's 4. How many diamonds? There's 3, right? So we get all of our counts, and this will tell us where we're going to start starting stuff in our final array, right? And then from our counts, we can say, okay, where are our starting indices? So we'll say, well, the clubs are the smallest thing, so they should start at the beginning, right? And then from there, I'll say, okay, then next come the spades, and the spades start after all of the clubs, right? And then the hearts start after all of the clubs and spades. And then the diamonds start after all of the clubs and spades and hearts, right? So I count up all of the things that came before me, and I use those totals to figure out where each suit should begin, right? So then at the end, we find the starting positions of each, and then we do one more scan of this entire array, and we place things in to the starting position, and then once we've placed something in from that suit starting position, we just increment our count, and then now we know the next place to put it, right? So what's interesting is what we'll do is since we're starting from the beginning and we're scanning all the way down as we place in, we'll place in like Lauren first, and then we'll increment the starting point for spades now. As we place more things in, since we're scanning all the way through, what does this mean about our sort? Like, what kind of like attribute is it going to have? Starts with an S. Yeah, it's going to be stable, right? So what we'll do is as we fill in, we know that whichever clubs came before other clubs, they're going to stay in that order. So if we look in our club category over there, we see Edith comes before Lee, comes before Bearman, right? So good thing to know about these types of sorts, right? So then, just so you know, I borrowed this from Josh Hub, so don't sue me. Cool. Does that make sense for the counting sort? Did anyone want me to go back through that? So we start, we get our counts. From our counts, we know our starting points. From our starting points, we know where to start placing stuff. As we place stuff, we increment our starting point. Yeah? And then eventually we run out of stuff sorted. So it seems like we're able to do this in n time, right? Is there some sort of catch? Something to think about, right? So let's go into where the catch might come from. So this is something called LSD Radix Sort. It's called least significant digit. And this is a type, this is basically an expansion on our counting sort, and it's going to take us to being able to sort more things, right? So the idea of something that's a radix sort is not all keys belong to finite alphabets, right? Before, our alphabet was 4 things, right? It was clubs, spades, hearts, and diamonds. It's finite. It's 4. That's how big it is. But not everything belongs to that. So take strings, for example. You would think, oh, strings, alphabet, that's 26 letters, we'll be fine. But the issue is we can keep combining letter after letter after letter, right? So a string is like many letters that come from a finite alphabet, but as you combine the letters of that, what's the longest string? I don't know. I actually don't know. I don't even know in Java. But theoretically, the longest string is infinite, right? So what are we going to do if we don't have like a limited number of things, right? We can't say, oh, how big is my array going to be, or how many things am I going to count? We just have to figure out another way to sort this. So here's some examples, right? If we have our keys based on strings, then how do we know which one comes first? How do we just place it into the right spot? Even if we take our example with our like smaller alphabet of just 4 suits, if we say, okay, let's say that those suits can have like, you can combine suits next to each other and say, well, I'm going to have things that are spades, spades, and then hearts, diamonds. It's going to make things harder from the start, right? But what we know here is that each component of our key comes from a finite alphabet. So we know that like each of the 2 digits in our hearts and spades things, that comes from an alphabet of size 4. So maybe we can use this knowledge as we move forward. So yeah, here's what we'll do. We're going to use this idea of the counting sort, and then we're going to start at the least significant digit. So the least significant digit is like the smallest thing. So like in numbers that we're used to, if we take any of these numbers, like say 9,918, what's the least significant digit? Is it 9, 9, 1, or 8? Okay, so least significant digit means it has like the least like influence on the size of the thing. So like the ones place is less significant than the tens place is less significant than the hundreds and so on. So our least significant digit here is 8, right? If I say 9,918 and our most significant is 9, right? Does that make sense? Okay, cool. So if we start with our least significant digit and we sort based on that, and then we move up to our most significant digit, maybe this will give us something we want, right? So what we'll do here is we'll say, okay, this is our starting list, and we're going to start with our least significant digit, aka our right digit, and we're going to sort based on that. So we take all of these things on this side, and we sort them just based on their right suit, and then we get to this middle list right here. So this middle list is like kind of sorted, right? What's important is that like if we have like our digits, like I guess here, something to think about. So if we know that the like clubs are less than the spades or less than the hearts or less than the diamonds, right? So if I have something that starts with a diamond versus something that starts with like a club, which one would you say is bigger? The diamond one, right? But right now when we sorted by our least significant digit, our middle array, we ended up with something where the diamonds are before the clubs, which makes it feel like, oh, we've sorted things in the wrong way because our diamonds are like considered to be smaller here. But what's important is this is just an intermediate step to our final sort, right? So what we'll do is we'll start at our least significant digit and we'll keep stepping up in terms of significance until we reach our most significant digit. So in this middle array, what we know is that our like second suit is going to be sorted correctly, right? We have our clubs, and then we have our spades, and then we have our hearts, and then we have our diamonds. So this is okay, but we've pretty much sorted by like the ones place, yeah? But what we'll do is we'll then move on to our next most significant digit, and we'll go ahead and start placing these in, right? So from this point, we say, now I'm going to do another scan through, and I'm going to take the clubs out, and I'm going to start putting the clubs at the beginning. And then once we do all that, we've placed Lee up at the top, Bearman up at the top, Edith up at the top, and we start placing it in that order. And what this will do is by the end, now it looks like our most significant digit is sorted, but our least significant wasn't, right? But what's important is that within each of the most significant digits, the least significant digits are sorted, right? So we kind of had like big ranges and then smaller ranges within, yeah? So what this does is it does actually lead to our final sort being in the correct order. And the reason it is able to do that is because we know that our intermediate step was stable, right? Because we didn't change the ordering on our way through, we basically said, I'm going to sort by like the less significant digit, and I know it's not going to be important right now, but in the end it's going to be really important. So we sort by the least significant digit, and then when we do our next sort, and we've sorted by our most significant digit, then within each chunk of the most significant digit being sorted, the least significant digits are still in the same order because of stability. Does that make sense? Are there any questions? Yes?
Basic question. Like, so we're sorting the keys, right?
Yeah.
What's the point of the values? Like, we're not alphabetizing them or encoding in a particular order.
No, but theoretically we could later, and like if we wanted to like treat the values as some sort of like other digit that we could use, now we can keep using these sorts, and like we can then sort by value if we have duplicate keys. Right now all the keys are just basically the key value pairings are just so that you don't have a bunch of like symbols up there that you don't even like. The words are just so that you can like attach them to each of the keys. Yeah. Yeah.
Where do you get the keys from in situations with strings?
Well, this is basically like if I dumped a bunch of like key value pairs in something and then I want to get them sorted by key, this is something we could do, assuming that we know the keys have like digit places. Yeah? Cool. Other questions for now? Okay, let's move on. So then that was an example with suits, which may have been kind of confusing because not everyone was familiar with what cards are. So then if we swap it out with numbers, right, and we just swap out, clubs become 1, spades become 2, hearts become 3, and diamonds become 4, then it starts to make more sense, right? If we then have our keys as numbers that we know, right, we know that 22 should be below, or should be above 41 at the end, like Lauren should be above Glasser. So what we know is our first sort puts Glasser above Lauren, which is like, what have we done? We've sorted by our less significant digit. But by the end, we know that Lauren's going to be in the right place there, and is going to be in the right place relative to like JF's. So what we do is we sort at the least significant, and then as we keep moving up, we're going to get more and more sorted order, and it's going to maintain the stability from the previous parts. Okay. So then the question that you want to be able to answer. Oh yeah, do you have a question?
What do you do if there's like different amounts of digits in each number?
Yeah, so we're just going to get to that in like a few slides. Yeah. So then let me know if it doesn't answer when we get there. But yeah, so the question for you to ponder is what is going to be the runtime of this LSD sort, right? So we were thinking before, how can we beat n log n? Now we have like a bunch of other factors to think about, right? So this is for tomorrow's lab, so you're like try to ponder it and think about it until you get to lab tomorrow. But things that you want to think about. How long is our array, right? We're going to need to look through like n things at some point probably. And then what's our size of our alphabet? Like before when we had just our suits, right? It was only 4 things, so we only had 4 chunks. What if we have a much larger alphabet, say the English language or something even larger? And then we have to think about the width of each item. As the last question we got was, like, what if the lengths of them are different? Like, should we use the smallest length, the biggest length, the average length, the total length? We have to think about how long each thing is, how many digits it has. So something to think about for tomorrow's lab. Cool. So this should get to your question, where we want to think, okay, what if we have keys that aren't all the same length, right? So in this example, we have things that are length 1, length 3, length 2, right? What do we do if we're trying to compare the next most significant digit, but there's nothing there? So in this first array that we created, we've taken the least significant digit of each of them and we've sorted it based on that, right? It's not quite sorted, so we want to get to the next significant digit, but 9 doesn't have anything there. Well, what we can do is we can start padding things, right? So what we'll do is if there's no digit before it, we can pretend that there's some sort of digit there that's always less than all the other digits. So what we'll do here is we'll go ahead and we'll pad everything. So now we take all of our entries and we make them all the same length, right? And what's that length going to be? Is it going to be the length of the shortest one, the middle one, the longest one? The longest, right? Because they all have to, you pad them up until that point. And there's no point in padding any longer than the longest one. So what we'll do here is we go ahead and pad it this way. Then when we want to sort in the next most significant digit, we'll say, okay, we'll sort on all those. 9 doesn't have anything there, so we'll pretend that that empty space is less than all the other entries, and we'll go ahead and shove that one to the top, right? And then when we move into the most significant digit at this point, we're going to go ahead and do the same thing, and we end up with it finally sorted, right? 9, 33, 43, 51, and so on. Does that answer your question? Cool. Any other questions so far? Okay, we'll keep moving on. So this is how we do our least significant digit, right? You start with the ones place, tens place, and so on all the way till you get to the end. This should work with strings, with numbers, with card suits, as long as you have things that you have digits and an alphabet size and then a final length and number of digits. So this should work. Let's try flipping it and going the other way, right? Will it work? Let's find out. So here are some long words. I can't read most of these words. Not because I wasn't taught to read, but because they're hard. But basically, how can we sort these in an effective way, right? Theoretically, if we use our LSD, we start at the end and we say okay, I'm going to sort on M and N and M and S, and then we're going to go S and O and S and U, and we're going to sort these super long words, right? But without even knowing what these, how to say these words or anything about that, I can tell you that there's, that one that starts with an A probably comes first, right? And then after that, it's the one with an F, I think. Yes, and then H, and then with the P's, I then have to look at the next digit, and I say, okay, N comes before S. Bam, I've sorted them. I didn't even have to look through all the digits, right? So that kind of argument right there, not really an argument, but me bantering, is why MSD might be useful, right? If we start at the most significant digit, since we know that has like the most power over the rest of the digits, maybe we'll get things sorted a lot sooner, right? So here's what we'll do. Let's start with the topmost digit, and then the middle digit, and then the rightmost digit. And then if you had more middle digits, you can sort all those two. But will we arrive at the correct result? Who thinks yes? Got a few. Who thinks no? Who doesn't feel like raising their hand? I feel you. So here's what we'll do. Let's just do it anyway and find out. So we're going to start with our most significant digit, right? And we sort by all the 8's, right? Already mostly sorted. Like we're almost there. Life's pretty good. Yeah? Now that we've got things all sorted by the most significant digit, let's sort things by the middle digit, right? Right here, we run into an immediate problem, right? ADD and ACE are supposed to be at the top of the end, but we have like BAD and CAB and FAD and all those things, right? And those, since their middle digit is less than the like AD and ACE's middle digit, they'll get pushed up to the top instead, right? And what this will do is we'll say, oh shoot, now we're thinking that like BAD is less than ADD, right? So, maybe it doesn't work, right? Any ideas for how we can fix it?
You could try creating auxiliary list based on the most significant digit.
Yeah.
A lot of the words, and then you would sort inside the.
Yeah, exactly, right? So what we can do is instead of just sorting the entire list, every time we like finish one of our sorts, we've basically created different chunks, right? We have the A chunk and the B chunk and the C chunk and the F chunk, right? Now for each of our chunks, we can go ahead and sort each one separately, right? So now that we have our A chunk and our B chunk and our C chunk and our F chunk, right? Then we take just the A chunk and we sort that by the next digit, right? So then we'll go into the middle digit and we'll say, okay, based on this, I'm gonna sort C comes before D, right? And then the B's are gonna do the same thing. B comes before, or BA comes before BE, right? So now I have 2 chunks here, and then same with the rest of them. But what'll happen is every chunk is gonna get its own independent sorting. So when we take the B chunk and we sort it by the middle digit, by the time we sort the final digit, we don't sort BAD with the rest of them, we sort each chunk independently. So we'll go through there and we'll only sort the part that needs to be sorted. And then by the time we get to the end, will it be in the correct order? Yeah. Okay, cool. So things to think about if this is MSD versus LSD. What are the best cases and the worst cases in terms of those like inputs that we came up with before? Again, for tomorrow's lab, gives you something to think about. So yeah, now we're going to be able to update our sorting runtime analysis table. So we have all of our stuff from before, and then now we're going to add in our like counting LSD and MSD, and then we're going to be able to know that they're definitely going to be stable. But then the question is, what are their runtimes going to be? How much memory are they going to take up? That's for tomorrow's lab. And then here's that little disclaimer over there at the bottom that says we can make them stable, but sometimes it costs runtime. And then in addition, because we're talking about the idea of like comparisons versus not doing any comparisons, like why would comparisons be bad other than like the fact that we're limited to n log n runtime? Part of the idea is, what if like when I make a comparison for an item, it takes like a certain amount of time? Like currently we've just been assuming like, hey, comparison, it happens. This thing's less than this other thing. You might have a situation where a comparison kind of takes some time. I don't know if everyone's looked at that KD tree idea, but you notice that like point distance, it like is a bunch of like math stuff that you may not understand. And basically that takes some time to compare 2 points to figure out like what their distance is and then see which one's smaller, right? So stuff like that means comparisons might take a while, so it might be harder to sort things. So it's going to be another thing that you'll have to factor in when thinking of comparison-based sorts. Cool. And then this is something cool you can click on if you have the slides, but basically, I have like a minute that I can show you. But basically, it's this cool algorithm where it's like, here's a bunch of sorting, and then it shows you, and you can look at them, and there's sound, and this is selection sort. So yeah, this is a good way to waste 6 minutes, not waste, to invest 6 minutes of your time. Yes. Okay, cool. Let's move on. What? Oh, break now? Cool, break now. You have 3 minutes to take a break. We'll watch the sorting algorithm in the meantime. Cool. go faster. Pretty fast. So the colors are which level of heat you're at. LSD, we just learned that one. It's pretty cool. So you see it gets sub-sorted every time we go through. Done. MSD. These are our subarrays. Cool. Stuff we don't know. That's some of these sorts of like bigger and smaller bars, because this one will take a really long time. So like do as many of the 100 items.
Hello? Can everybody hear me okay? Yeah? Alright, cool. So I hope you guys enjoyed that video. I actually really like it a lot because it's very soothing to listen to and to see everything get organized. So you can always visit it again if you want. Countersort, I think that's the one that just like randomizes things and tries to randomly place everything and hope that it works. So that's why I didn't really go anywhere. Okay, so now we're going to completely take like a pivot here and talk about something different related to graphs, which is what we talked about, I think, last week. And we're going to talk about this idea of minimum spanning trees. Okay, so I'm just going to start with a definition first. We'll see how this ends up being useful later on, but let's first talk about what a spanning tree is. All right, so note that this will only work on what is an undirected graph, so graphs without any arrows on those edges. But in an undirected graph, a spanning tree will basically follow these three characteristics. So it has to be connected, it has to be acyclic. That's what makes this graph tree. And then the last thing is that it has to include all the vertices. So it has to touch every single one of them, and that's where the spanning part comes in. So these two definitions are for the tree. This one is for spanning. So in total, if we have this subgraph that has these qualities, we have what is called a spanning tree. All right? So in this example over here, we have a graph, and all these edges that are in black represent what the spanning tree is for this graph. So note that there can be like a lot of spanning trees. So for example, this edge 8 right here, we could have replaced it with like this edge, or this edge, or this edge. There's a whole bunch of edges that we could have picked, but this is just one example of a spanning tree. Okay? So another thing that we can put on top of that is maybe we want it to be the minimum, for example. So let's say that each of these dots on here were instead buildings, like buildings on campus, and each of the lines that aren't, don't worry about the black versus the gray lines, but every single one of those edges represents connecting those two buildings, and we want to create like a power network between the two, or between all the vertices really. So all of these edges will represent ways that we could connect them. Let's say that creating those connections does cost money, so we want to minimize the amount of money that we spend to connect everything to each other. Right, so this is an example of why we would want the minimum spanning tree. So we have this idea, we have a spanning tree, we can make it a little bit more constrained by adding this minimum thing onto it. So if we want to directly connect buildings by power lines, each of these are power lines, we could just generate the minimum spanning tree of this graph that represents our buildings, and then we can figure out which power lines to build. Right? So this is not really, I don't know if this is an example of the minimum spanning tree here, but this is one of the possible configurations that you can make. Okay, so here are a few more examples of just spanning trees in general. These don't really have any edges on them, or sorry, they do have edges. They don't have any edge weights on them, so we can't tell which one's the minimum, but we know that these all count as spanning trees. So in this example, we can see that all the edges, or all the vertices are connected to each other. There's no cycles here, everything is connected, so this is an example of a spanning tree. This one is also an example of a spanning tree. So you can see that they can come in very different shapes. This one is what we would call very like spindly. It's kind of just one line that is connected to each other. But this one is a little more bushy, right? This one has more edges coming out of here. Note that a spanning tree, we don't really care about whether it has this spindly structure or it has this bushy structure. We just want it to be connected. Okay, it's whatever, for us we want the minimum, so whatever brings us the minimum, that's what we'll go with. But we don't have to have this one, which is the bushier one, versus this one, because it doesn't really matter for our scenario. Okay, so now we have a few more spanning trees. So I'll give you guys 30 seconds to just think about it. For every single one, determine whether it is a spanning tree or not, and if it's not, determine what's wrong with it. All right, so I'm going to ask you guys which one is and explain like what's wrong with each of them, so make sure to come up with something. So 30 seconds, and then we'll talk about it. Okay, so let's bring it back. I hope you guys have had at least some time to think about this. So let's start with this one. Is this one a spanning tree? Who thinks yes? All right, how about no? Cool. All right, so what's wrong with this? Can somebody tell me what's wrong with this one? It's not connected, right? So this one is not connected. This is kind of like one tree is over here and one tree is over here. So this is not a connected tree. So this is not what we call a spanning tree. Perfect. All right, what about this one? Is this one a spanning tree? Yes? All right, what about no? Great. Okay, so what's wrong with this one now? Can somebody tell me? Yeah, cycles, right. So I'm kind of hearing it around the room, but this one is because there is a cycle that's existing with these four. All right, so what about this one? Is this one a spanning tree? What do you guys think? Yes? What about no? Okay, perfect. So this one is an example of a spanning tree. It follows all those three characteristics that were listed on the previous slide. I'm not going to go into that, but this one is an example of a spanning tree, this bottom one here. All right, perfect. So now we're going to talk more specifically about minimum spanning trees. Here are some applications. So in addition to our building thing, here are two other ones that are used in the real world. I don't actually know too much about them, but you can actually use minimum spanning trees to take handwritten equations like this and convert them to like the LaTeX version of this. Like there's an algorithm that some grad student has invented like a long time ago that does this using minimum spanning trees, which is really cool. You can look at the paper that's right over here if you're more curious about that. But you can also image what this is basically skin cells right here. So this is the nuclei of the skin. You can show how they're connected using a minimum spanning tree as well. So it's a lot of cool things that aren't just specifically trying to connect buildings together. So if you're curious, you can look at more minimum spanning tree applications that are right over here. Personally, I'm not too familiar with these two, which is unfortunate, but these are all really cool ways that you can use minimum spanning trees. All right, so now we're going to just go through a series of questions just randomly about minimum spanning trees. First one is, find the MST for this graph, all right? So remember those three characteristics. It has to be acyclic, it has to be connected, and they have to like touch all the vertices or something. I can't remember all three of them, but you guys probably know. But figure out what the MST is for this. I'll give you guys 20 seconds for that, and then we'll come back together and we'll expand upon this in a bit. All right, cool. So let's bring it back. So the MST for this graph, we can kind of just stare at it and try to figure out what it is for this one, but we'll be using all of these edges right here. So one way that we can figure that out is, why don't we use this 3? If we swap this 3 edge for any of the other ones that are in here, we'll actually not follow some of those properties, right? So if we had, instead of this edge, AB, we did AD, then this would not be the minimum spanning tree anymore. So this is, the example. This is the minimum spanning tree for this graph. There aren't any other ones for this graph in particular, but note that there is a possibility that there can be multiple minimum spanning trees for a single graph. All right, so next question is, we know that our minimum spanning tree of this graph looks like this one right over here. All the 2 edges are used. There's also this idea of what we call a shortest paths tree. So remember back to last lecture, we talked about Dijkstra's algorithm that provides you the shortest path to every single vertex in the graph from a starting point. And that actually generates a shortest paths tree out of it. So I don't know if we like really hit it on last lecture too much last time. So just note that there is this idea of a shortest paths tree. So what that means is, starting at some vertex, maybe A, there you can generate what is called the shortest path tree. So the shortest path from A to everything else, okay? So I want you to figure out which shortest path trees are the same as the MST. So we know that our MST looks like this. We know that there are shortest path tree that exists for every single one of these vertices. So we want to figure out which shortest path tree is the same as the MST for this graph, okay? So we can have 4 different starting points. So let's go through the D starting point together. So for D, the shortest path tree is actually this graph right over here. So D to C, D to B, D to A. We don't want to use this one, this path, because its length is 4, but we can get a shorter length with 3. So we know that D is not an option, right? So now I want you to figure out for C, B, and A whether those shortest path trees will be the same as MST. So kind of employ the same tactic that we did here. Start at whatever vertex and see what the path should be, and if that matches the MST. All right, so I'll give you guys maybe 30 seconds to do that. Just try to get the general idea of it, but we'll come back together in around 30 seconds. Okay, so let's bring it back. I hope that question wasn't too vaguely phrased, but does anyone have any idea of what the answer could be for this one? Is there any vertex that counts? Yeah, Mertz? B? All right, perfect. Yeah, so the answer is B. There's a lot of different graphs on here, but if you kind of just try it for every single one of those vertices, you'll see that A's shortest path tree looks like this, B's shortest path tree will look like this, and C and D's will look the same, which is this bottom one over here. All right, so just note that what this exercise, what we wanted to tell you is that the shortest path tree depends on the start vertex because it tells you how to get from one source to everything else, right? It's truly dependent on where you're starting. There is not really an idea of a source for a minimum spanning tree. We don't really start in any particular place. It's just this idea of how can we connect everything the best way that we can. We're starting at 0, how do we connect everything? We're just trying to connect all the things, all the dots together in the minimum way possible. So there is no idea of a source in a minimum spanning tree. In addition, sometimes the MST ends up being the shortest path tree for some, but we saw in those other vertices that didn't work. Right? So just note that sometimes coincidentally, that shortest path tree for some vertex will end up being the same as the MST. All right? So just some things to keep in mind. It's easy to conflate the two, to kind of mix them up, what a shortest path tree is and what an MST is. But just note that there is this difference in that sometimes they're the same and sometimes they're not. Okay, so before we move on to the next point, does anyone have any questions about anything that we talked about so far? All right, perfect. So now we're going to talk about generating these trees, right? It's really nice to have this idea, but we want to be able to create these trees somehow. So we're going to jump into a little bit of graph theory here, so just bear with me. This is a very useful tool on finding a minimum spanning tree, and what this is called is the cut property. So we're going to define a few terms here. The first one is what we call a cut. So a cut, it says that it's an assignment of a graph's nodes to two non-empty sets. It's a fancy way of saying let's color each of the nodes and say, okay, we have the gray set and then we have the white set. So you're just taking the vertices, putting them in two sets, and this is what we call doing a cut on the graph. All right, so here is our cut here. We have this one set here, this other set here. So you can see that there is a cut. We can actually visualize that cut right down the middle, but just note that it doesn't have to look exactly like a straight line cut. This one could have been white as well, so we'd have kind of a weird cut going on here, but it's just a partitioning of the vertices into two sets. Okay, so the next term that we'd like to introduce is what we call a crossing edge. So a crossing edge is, the definition here says it's an edge which connects a node from one set to a node in another set. So in our example here, it's just connecting a gray node to a white node somehow. So all these in red are what we call crossing edges. All right, so cut is taking those vertices and putting them in two sets, and crossing edge is those connecting the sets together. All right. The cut property is what is listed down over here. So given any cut, the minimum crossing edge is said to be in the MST. So we're not going to go over like a super in-depth proof. We'll look at a really small one later on, but this is more focused like CS70, CS170 stuff. But this is just an introduction to see why does this idea even work. It's because of this cut property thing. So any cut, if we are given any cut, the minimum crossing edge is the one that will be in the MST. So for example, if this edge were the minimum out of all these red edges, this edge would have to be in the minimum spanning tree. Okay, so we'll see a lot of examples about this later, but just kind of take this in right now, and then we'll try to explore a little bit why this actually works. Okay, so we'll go through an example here. So cut property in action. We have another cut. This is the one that I was talking about before, that we have these white nodes and the purple ones. So this is a valid cut, even though we can't really see one straight line. The cut is around this 5, and then we go around this way. All right, so there is a cut that exists here. And which edge is the minimum? All right, so these are all the edges. The numbers, don't worry too much about how they were generated, but figure out which edge is the minimum weight crossing edge across the cut. All right, so I'll give you guys 40 more seconds to just think about this. Remember that these are actually in sorted order, so try to go down the list and see which one satisfies that property. All right, so go down the list, figure out which one's the minimum, and then we'll talk about that. Okay, so let's go over this one. I think this one might have been a little bit hard because there's just like a whole lot of numbers on this screen. So let's go through this one together. So we'll start with the first one. We'll go down the list until we find a crossing edge. So 0 to 7 is at a crossing edge. They're both white, so we know that they're in the same cut, so it's not a crossing edge. All right, so that one knocks 0, 7 off the list. Now let's try 2, 3. Is that one a crossing edge? What do you guys think? No, this one's not a crossing edge. Both 2 and 3 are purple. Yeah, purple. So that one does not count as a crossing edge. 1 and 7, does that one count? No, that one is also, they're both white. 0 and 2, what about this one? Yeah, so I see a bunch of head nodding, which is good. And that means, like, this one is a crossing edge because 0 is white, 2 is purple. So they're two vertices that are from different cuts. So this will end up being the minimum weight crossing edge. And this will be the edge that is included in the minimum spanning tree. So this is the cut property in action to help us determine what a minimum spanning tree is. Okay. So I got a question in the break that how do we determine these cuts? Because seemingly it looks pretty random right now. And we'll actually figure out, like once we see the algorithms later on, we'll figure out a very systematic way to determine these cuts and how to figure out this is part of one set, this is part of another set, and doing that idea. So we'll see in a little bit what the algorithms look like, so hopefully that'll make a little bit more sense when we get there, but just let me know if not, and then we'll talk more about it. All right, so this 0, 2, we're following the cut property here, so 0, 2, this edge must be the minimum spanning tree. Right? That's the minimum weight crossing edge across this cut. Okay, any questions about this cut property thing so far? Okay, cool. So we'll keep moving on. The next part is just, this is the small proof that I was talking about before. It's going to be very hand-wavy-ish. We're going to do a contradiction. You'll learn more about this when you take CS70 and other classes that talk about graph theory, but let's just try to do a proof by contradiction to see why this actually has to be in the minimum spanning tree. All right, so let's say that we have this cut. We have the gray nodes here, the white nodes here, so this is the cut. And suppose that E, this dotted line E, is the minimum crossing edge. All right, so let's just suppose that it is the minimum. We don't know that, we're just like saying that it is. So E is a minimum crossing edge. Oops. And let's say, just for now, that the minimum crossing edge is not in the MST. Right? We're trying to make a contradiction here, so let's assume something that we know is wrong. So we're assuming that E, the minimum, is not going to be in the MST. All right? So we know that if E is not in the MST, that means that adding E must create a cycle, right? Because there must have already been a connection that was better that we found before, okay? So adding E to the MST must create a cycle, like it's wrong that we added E. And that some other edge, maybe F, is the crossing edge that is connecting those two sets, all right? So we're assuming that there is already another connection that is connecting these two sets together, and that connection is not E. But that connection is F, and it's not the minimum. Right? The thing that we can do here is that we know that if F is already connecting us between these two sets, and F is greater than E, why don't we just remove F and add E, and we'll get a lower value. Right? So this is where the contradiction is happening, is because we know that F is larger than E. That's how we set this problem up, is that F is not the minimum, E is the minimum, but E is not in the MST. Right? So we're setting this up, but we know that we set up something wrong because we can do this operation. We can remove F from the minimum spanning tree, replace it with E, and we'll get something that's even better than what we had before. All right? So we know that this assumption that we made in the beginning cannot be true. Right? This is a contradiction because we're saying that the minimum edge E cannot be in it, but adding E will end up making it better. So we know that this is a contradiction. This crossing edge E must be in the minimum spanning tree. So that means that every minimum crossing edge across every cut must be in the minimum spanning tree. All right, so it's a little bit hand-wavy. It's just a contradiction proof that you'll definitely learn more about in CS70. So if you don't feel too confident about that now, that's totally okay. But did you guys have any questions about this before we move on to looking at how the cut property works? All right, cool. So this stuff is kind of confusing. If you have any questions, I'll also be here afterwards to talk about this too, but just take this for now that the cut property works, that the minimum crossing edge across a cut must be inside the MST, all right? Because we're going to use this to help us develop those algorithms. All right, so the next part is just how do we generate this minimum spanning tree finding algorithm? All right, and what we said is that we can use this cut property to help us find those edges. So one thing we can do is we can start with no edges, have an empty minimum spanning tree so far, find a cut that has no current crossing edge inside the minimum spanning tree, add the minimum, and repeat. Right, so just find a random cut and then add the minimum. Find a random cut again, find the minimum, and so on. So we're going to repeat this process over and over again to help us find those minimum spanning trees. All right, so now the question is, how do we find those cuts? Right, we can't just like randomly pick cuts because that's probably not the best way to go around it. You might end up revisiting the same cuts over and over again. You might, I don't know, you'll probably do something wrong if you end up doing it the random way. So we'll go into 2 ways to actually do this with a very systematic way of finding those cuts. Okay, any questions before we move on to that part? All right, great. So the very first one that we're going to start off with is what we call Prim's algorithm. So we're going to learn about 2 algorithms. We're not going to go into them in like super code depth or anything because that's actually the assignment for next week. There's going to be a minimum spanning tree lab that you'll actually do all the implementation of these algorithms. So here is we're just trying to introduce them to you. So if we kind of go on the surface level, that's the reason is that you're going to get more experience with these when you do it in lab next week. All right, so this first one, I'm not going to actually talk about whatever is on this slide yet. I'm going to go into this demo first so we can get a conceptual idea of how this Prim's algorithm works. So hopefully this loads. All right, perfect. So this is the procedure that we'll be using for Prim's algorithm. So we're going to start from some arbitrary start node. We're going to add the shortest edge that has 1 node inside the MST, and we're going to keep doing that over and over again. So it might seem a little bit vague right now, but you'll see conceptually in a little bit, and then we'll talk about it. I'll ask you if you have any questions too. So we'll start off, let's say that we start at 0. So we're going to start at the 0 node. And from the 0 node, we mark that to be as a part of our minimum spanning tree. And then this is this operation. So we're going to add the shortest edge that has 1 node inside the minimum spanning tree, and the other one is not. Right, so here's the white nodes are the ones that are in the minimum spanning tree. The green nodes are the ones that have not been. So we're going to take a look at these 2 edges here. All right, so this is where the cut is happening. So you can see that the sets is the white nodes and the green nodes. So there is a cut that exists right over here. Okay, so which edge are we going to pick? The 1 or the 2? Which one's the minimum, 1 or 2? 1, great. So we're going to pick this edge, right? We're picking the shortest edge that is across this cut. So we're going to end up choosing this edge right here. 2 becomes white, and now we have a different cut here. So we have these 2 being white and these all being green. All right, everyone following so far? Okay, so the next thing is we're going to do the same procedure again. We're going to see what edges can we possibly choose from, which ones are across the cut, so that those are the ones that are over here. Which edge are we going to pick? Which one's the minimum out of all these pink edges? 1, yeah, so here's 1 again. We're going to pick 1, 4 becomes white, so we now have another cut. We have this cut right over here, and we're going to repeat that 1 more time. So we're going to have all these pink edges, right? All of them are things that we could pick from. This 15 actually shouldn't be pink because it's, wait, actually this is okay. So we have all these pink edges. These are all our options for what edge to pick next. So what's the minimum of all the pink edges that are on here? 2. Yeah, so the problem is that which 2 are we talking about? Right? There's this 2, there's this 2 here. So what do we do when we have this kind of duplicate error? It's not an error, it's just like, how do we deal with duplicates here? It actually doesn't really matter which one we pick. We're not going to talk about the proof for that, but either one of these 2 edges could work here. So we're just going to pick this top one right over here. But just note that we could have picked this one as well. All right, so it doesn't really matter too much For our case, either one of those edges could work. All right, so now we have another cut one more time. We have the white edges, or the white nodes and the green nodes, so the cut is kind of this weird loopy thing. So we're going to now consider these edges. The minimum in this case is going to be this one over here, so the one will be picked. More pink edges, and then we're going to pick this one right over here, and then all these pink edges, we're going to pick this two over here. So this is the procedure of Prim's algorithm. It's starting from some vertex. I know we said we wouldn't start somewhere, but this is how this algorithm works, is you just start from somewhere, and the cuts will develop as you add things to your minimum spanning tree. All right, so any questions about this conceptual demo? All right, perfect. So we're going to go back to here and resume what we were talking about for Prim's algorithm. So this is what we did. We just started at some arbitrary node, and we just kept adding the smalls that we were connected to so far. All right, so hopefully that conceptual demo made sense. You can read here, like, why does Prims work? It's because of that idea that we are creating cuts, right? Every single time we're creating a set of white nodes, set of green nodes. The white nodes is part of our MST so far. So that's where the cut is being created, and we're choosing the minimum that we're connected to. All right? So hopefully that made sense. We're going to keep going just for the interest of time, but you can take a look at these two visualizations for how Prim's algorithm will end up exploring a graph versus how Dijkstra's will. All right, so we can see that this procedures seem very similar to Dijkstra's. We're going to explore it a little bit more, but they explore the graphs in very, very different ways. Right? It's a very similar procedure where we kind of like are relaxing the edges all the time, but this one ends up exploring it in a very spindly way, while this one kind of looks like, I don't even know how to describe this, kind of looks like a web. But we'll see that their algorithms are very similar, but you end up exploring them in a lot of different ways. So you can visit this if you ever want to see this again, but here's how the implementation will work. So we kind of talked about this already, is that this natural implementation, like the conceptual way that we did it, is a very natural way to approach this Prim's algorithm. The problem is that picking all those purple, pink edges, looking over them every single time is very, very inefficient because, yeah, you can just tell. Like, there's a lot of edges here. There's a lot of ones that we didn't consider. So we can actually use some cleverness and a priority queue to speed this process up. So this is why I'm alluding to Dijkstra's right now, is that you'll see in this demo right here that it is very similar to Dijkstra's. So we're going to come to this demo. I'll open this. And then we'll just step through it again. So we're doing the same graph, same thing, but now we're going to use some of the things we learned from Dijkstra's to help us figure this out. All right, and to do that purple, pink edge picking, we're going to do that a little bit faster this way. Okay, so instead of just starting from one place and saying, what edges are pink? We're going to use a priority queue to tell us this information. All right, so we're going to start with 0 again. And we're going to look at these two edges, right? These two edges are pink because we're currently taking a look at them right now. And then we're going to see what is the shortest distance that we can get to these two vertices, right? Because that's basically going to hold this the pink edge information that we had before. So I know that's a little bit vague, but we'll see that once we evaluate these two edges, we know that their current distance from the tree so far is infinity. Like, we haven't seen anything before, so these two edges will be better than what we know. So what that will do is that we'll update 2's value and 1's value in the fringe to be their distance to the tree. All right, so it looks very similar to Dijkstra's right now, but we'll see the differences in a little bit. But what we did is that we started at 0. This is our minimum spanning tree so far, and we're trying to see if these edges will bring these vertices closer than we knew so far. Okay? So we know that 1, instead of being infinity away, it's now possibly 2 away with this edge. And we know that this 2, it was infinity away, but it's now possibly 1 away with this edge. Right? And that's why we have these as being dotted. Right? The dotted lines will mean that we are considering these edges. Maybe they're part of the minimum spanning tree. We don't know yet. But we'll see as we progress through the algorithm that they will eventually just get picked slowly and slowly to be included. All right, so this next one is we're going to do the same thing that we did in Dijkstra's, where we would take something off the fringe. So this 2, 1 will be the next one that is popped off. And then we're going to evaluate all the pink edges. Right? We're going to evaluate all the pink edges and see if these edges will bring vertices closer to us. Right? So if we evaluate this, we know that through this edge, we can reach 1 in distance 5. But we already know that we can reach 1 in distance 2. So there's no reason that we want to update this knowledge about 1. We have an edge already, which is this one right over here, that is the minimum edge if we wanted to connect 1. So we don't want to update this, but for both of these, this edge to 4, this edge to 15, they are both better than what we already know so far about 4 and 5. So those will be updated. All right? So just note that the fringe, it's not keeping track of the distance to that node. It's keeping track of the distance from the tree so far. So we know that this 4, it's actually distance 2 away from the start. So we started at 0, the 4 is distance 2 away. But what we want to know is how far is 4 away from our tree so far. Right? We don't care about how far it is away from the source. We just want to know how far away are you from the tree so far, because that's what we want to do. We want to connect the minimum spanning tree in the minimum weight. We don't care about like how long those paths are. We just want the total minimum weight. So that's why we're using inside our fringe the distance away from the tree so far. All right? So we can see that this 4, its distance from the tree is 1. 1's distance away from the tree is 2. And even though that this path from 0 to 4 is not 1, we're trying to see the distance from the tree, not the distance from the source. All right? Does everyone see that? Does anyone have questions about that? Okay, so we'll go through the next parts pretty fast, just for the interest of time. So we're going to next pop the 4 off. So 4 is mapped to 1. We'll see that, so 4 is the next one that's going to be popped off. So I'm just going to skip over this one right over here, but we'll pop off 4. Then we'll evaluate these edges and see if those are better. Right? We have current distance to 1 is 2. We have a distance of 3 here, but we won't update that because it's not better. The other ones we'll have to do an update because here, this 4, we have an edge to 5 that's of distance 4. What we know is 15, so that one's better. So we'll end up swapping this one out right here. Right? And here, those will also be updated as well. So a lot of things will be changed here. Okay, does anyone see that? Does anyone have questions? All right, cool. So if you ever have questions about how this will work, like once that lab rolls around next week, always refer back to this because this is a pretty good place to start if you want to implement prims. So you can see that it is quite similar to Dijkstra's, but there is one small difference. All right, so I think I was alluding to this a bit, but prims and Dijkstra's algorithms are pretty much exactly the same, but Dijkstra's will consider the distance from the source, while prims will consider the distance from the tree. Right, so that's the biggest difference is what you're adding to the fringe, what you're keeping track of, because we're not keeping track of the distance from the source anymore. We're keeping track of the distance from the tree. So the visit order is the same. It's pretty much the same. Relaxation is very similar, so you can take a look at the differences there. But we're basing our entire procedure off of distance from the tree rather than distance from the source. So just keep that visual in mind as you're coding it next week in lab, that you're trying to get the distance from the tree rather than from the source. And that's really the only difference. Okay. Any questions about prims before we move on to this next one? Yeah.
So it was almost identical in Dijkstra's, but in Dijkstra's you could like return a path to from start to end. So what is prim to return since
Okay, so the question was, in Dijkstra's, we were mostly looking for the shortest path from one place to another. So our return value would be like that shortest path, A, B, D, F, or something along those lines. In this case, we're going to be returning the minimum spanning tree. So it really depends on what your problem looks like, what format that you want it to be in. Maybe it'll be a series of edges, or maybe it'll just be the total weight or something like that. But it'll be really clear in lab what they're asking you to return in the end, and it really depends on what you want, because sometimes you might just want the weight, or sometimes you might want which edges are in the graph. Okay, so I'll go through this one a little bit more quickly. I think it's a little more straightforward than this last one. But Kruskall's algorithm is, I'm not going to go over that part yet, but I'm just going to go through a conceptual demo like we did in prims. So this is the Kruskall's one. once it loads. All right, cool. So Kruskal's algorithm is a little bit more, it's what we call a greedy algorithm. So what it does is it sorts the edges from least weight to the largest weight, and then it'll just go through the edges in order and say, let me pick this one. Is this one possible? I'll add it. So it's going from the smallest edge to the largest edge, adding it if it fits in the MST. All right, so it's a little bit, I think, more easier to conceptualize. So let's take a look at how this would run. So we have all of our edges. They're listed here. They're all in sorted order. So these are the 1 edges. This is 2, 3, 4, 5, 11, and 15. So we'll start with the first one, 0, 2, and we'll see, okay, can we add this to our MST? We can, because the problem with MST is we just don't want to create cycles, right? We want to make sure that we don't reconnect something that's already been connected. So at every single edge, we'll just do this check. 0, 2, do we create a cycle? No, because 0 and 2 are not connected yet. So this one's good. All right, so now we're going to consider 2, 4. Can 2, 4 be in this MST? Yes, because there's no cycle, right? Making this 2, 4 does not connect something that is already connected, so that one is added. 3, 6, we can do the same thing. 5, 6, we can do the same thing. 0, 1, the same thing will happen. And 4, 1 is where we first find the first problem here, right? Because 4, 1, we're going to check, okay, 4, is it connected to 1 already? Yes, it is, through this path right over here. And then we'll decide to reject this edge and move on to the next one. All right, so we're just going to start from the beginning, go down the list and say, is this one going to create a cycle? If yes, we'll skip it. If not, we'll add it. All right, so this was, I think, a little bit easier to understand. And I didn't really talk about this too much, but you can see that every single time we consider an edge, there is a cut of white nodes and the green nodes. So when we're considering this 5, 6 edge right here, the cut is this one, 5, and all these are green. Okay. So I'm going to go through to, we just skipped this edge. We're going to consider 3, 4 now. 3 and 4 are not connected because they're in 2 different sets. So that one will be added. We're at v minus 1 edges, which means that we are a tree. So we're done here. So you don't have to look at any of the other edges. All right. So this one is a little bit more straightforward, I think. You're starting just from the smallest edge, going to the largest one, and adding it as we go. All right, so the next question is, how do we determine whether we have a cycle or not, right? Because we kind of can just eyeball it here and figure out, oh, those are already connected, or, oh, those are not connected yet. So the question is, how do we determine whether the cycle already exists? We'll actually explore that in lab, so I'm not going to talk about it too much here. But there are many different ways that you can do it. In lab, we'll show you one of the fastest ways. So I'm not going to talk about it, but it'll be cool. Okay, so this is the algorithm that we kind of just went through. We initially mark all the edges to be gray, which means it's not in our MST. And then we'll just consider the edges in increasing order of weight. So we're going to start with the smallest one, see if we can add it, go to the next one, see if we can add it, and so on, until we have all the edges. Right? Okay, so now we learned 2 of these algorithms. Hopefully that you've gotten like the general idea of them, but we'll go way more into depth once lab goes on next week. But we can see how these 2 explore the graphs, right? So we saw prims already, but look at how Kruskal's ends up exploring it. It's very different. It kind of like just places a bunch of edges randomly around, and that's because it's starting with the smallest and going towards the largest, right? So prims, it's starting from one place and expanding from there, but Kruskal's is kind of going all over the place, all right? So they will actually end up both forming minimum spanning trees. They might not necessarily form the exact same one if there are multiple options, but just note that it's very different how they're exploring it. But they both end up producing the same thing that we want in the end, which is a minimum spanning tree. Okay, so you can keep, if you want, you can look at this until it's finished, but I'll move on to the next slide, which is, now what is the runtime of these? I'm actually going to take like a cop-out, and we're not going to talk about it during lecture right now, but you'll have all the time to explore the runtime when we talk about it in lab. Just note that prims is very, very similar to dextrous, so you can kind of see where the runtime will come in there. Kruskal's, there's a few other things that we'll have to worry about, so the runtime is not immediately clear right now, but we'll talk about it a lot more in lab, and you'll see exactly what the runtime ends up being. All right, any questions about minimum spanning trees before I hand it off to Matt? Okay, perfect. So just note that we'll be here. So if you have any questions about minimum spanning trees, just let us know. But Matt will now talk about regular expressions, which is pretty cool. So I'll let him explain it.
Okay. All right. So regular expressions for the last part. This is going to be your last lab, so we're almost there. Oh, not mine. Okay, cool. So what is a regular expression? A regular expression, or regex for short, is basically a pattern string that can be used to match against or defined in a query string, right? So basically we have a pattern and you have a query. So for example, if I go like this, so humor me for a second. Nobody? Oh, perfect. Lovely. I used to teach like little kids, so this brings me back. So anyways, basically, you guys are trained from when you're really young to respond to that pattern, right? And you like in your brain, you're like, oh, match. Like I know, I recognize that pattern and that's a match. So that's basically the same thing we're trying to emulate here, right? We have a string and we want to see whether it matches a certain pattern or not. So for example here, if I have a pattern AT, then that matches the word AT, obviously because they're the exact same, but it doesn't match cat or hat. And that's because cat and hat are both longer than at. They're not exactly the same, so these queries, cat and hat, don't exactly match the pattern at. However, you can also ask to find the pattern inside a longer string. So alternatively, AT is in at, and it's also in cat, and it's also in Matt's hat, right? And so basically, find says, is this pattern, can the pattern be found in the substring of the query? Whereas you can also ask in the first situation, like, does the pattern fully match a query string, right? So first one is fully matched, the second one is there a substring that matches, okay? So these are the two different questions that can be asked. Okay, so if this is all that regular expressions can do, if it can only do a literal match, that's pretty lame and we can't do a whole lot. But luckily, there's a lot more expression that we can do. So, for example, we have character classes. So these are special characters that allow us to kind of have like a controlled wildcard in a sense, right? So you can do \d to signify that you want any digit to be allowable. So 0 through 9, any of those numbers would be allowable if you use that in your pattern. Similarly, you can use \w to signify that any word character is acceptable. So any letter of the alphabet A to Z, lowercase or capital. You can do \s to indicate that any single white space character is acceptable. So like the space bar or a new line character, those are both white space characters. Or you can use the dot, the period, to signify that any single non-new line character is acceptable. So that's basically anything except for a new line character. Okay, so for example, the patterns \WAT, so \W is a special character, right? So this is not WAT, this is \WAT. So that \W means any single word character is acceptable, and then followed by AT. So that means any letter and an AT is acceptable. And so that means cat and hat both match that because C is a letter and H is also a letter, followed by AT, right? But AT by itself does not match because there's no letter that comes before AT, right? And also note that .AT also works as well because that's just more things are allowed, right? You can have 0 AT and that will match .AT, right? Okay. So a special side note, the \/ character is actually a special character not only in regex, but also in Java as well. So if you want to use regex in Java, you actually need to use 2 backslashes in a row. So in normal regex, it'll just be \d, but if you want to use it in your Java code, you'll have to do \d. Okay. All right. Are we cool so far? Yeah? Yes? Question? Escaped. Escape just means like it's signifying a special character, right? So if you just put W, then that'll be literally the character W. But if you do a \, that means I want to use W as the special character instead. Yeah. So because \/ is a special character in Java, you also need a double \/ to say it's special. It's extra special. All right. What else can we do? We can have quantifiers. So quantifiers allow us to say that we want more than one thing, right? So if we follow something by an asterisk, a star, right, which is Shift 8 on your keyboard, right? So this star signifies that you want 0 or more of the thing that came before it. Okay, similarly, a plus means 1 or more of the thing that came before it, and question mark says 0 or 1 is allowed. Okay, so in this example here, W slash, remember that means any letter character, A to Z, or any word character, right? And then followed by a plus sign. So plus sign means that we are allowing 1 or more of any letter character, then followed by AT. Okay, so that means cat, that's 1 letter of any kind followed by AT, so that works. And then TH, AT also works because that's 2 letter characters followed by AT, and 2 is 1 or more, right? So that's allowed. But AT is still not allowed because 0 of backslash W is not allowed. Okay, so these are for full matches. Okay. Okay, I know there's a lot of rules, and you'll see these rules again in your lab, so just try to understand the spirit of what we're doing here. You don't have to memorize everything yet. That'll be next week when you have to memorize stuff. Or just put on your cheat sheet. Okay, here's an important concept, greedy versus reluctant. Okay, so by default, quantifiers, so what are quantifiers? Quantifiers are these things that we just saw, these multipliers, right? By default, they're greedy. So that means it will prefer to satisfy the pattern using as many characters as possible. They're greedy, they're super hungry, they just want to eat as many characters as possible. So in this example here, if I do M dot star AT, so remember dot means anything except for a new line, right? Followed by star, so that means what? That means 0 or more of the dot is allowed, right? So if you do Matt's hat, is it going to match MAT or is it going to match MATT apostrophe S space HAT? Well, it turns out it's going to match the whole thing because there's an M in the front and then there's all these characters in the middle which satisfy the dot star and then there's the AT at the end. And because it's greedy by default, it's going to try to satisfy it using as many characters as it can rather than just simply MAT. Okay. Does that make sense to everyone? So M dot star AT, because quantifiers are greedy, it's going to go for the larger one, the larger option instead of the smaller one. Okay. So the opposite of greedy is reluctant. So if you want it to be reluctant, meaning that it's going to be as conservative as possible, then all you do is add an extra question mark after it, and it'll switch to a reluctant mode instead. So the same query as before, or sorry, the same pattern as before, but with a question mark after the dot star, makes the star behave reluctantly instead of greedily. And so when you hit it against the query Matt's hat, it will go for the shorter option instead of the longer option. Okay? So by default, it's greedy. If you put an extra question mark after the quantifier, it's going to be reluctant instead. Okay? All right. Okay, a capturing group. So sometimes you find a pattern, but you don't want the whole pattern to be returned back to you. You're only interested in a specific part of that pattern. So for example, here, if I have a similar query as before, I'll keep saying a similar pattern as before. So M dot star AT, if I already know like M and AT are like not that important, I'm only curious about this stuff I don't know, this like mystery stuff, I can surround it in parentheses, and then I can use some Java functions to fetch back only what's inside those parentheses. Right? And so if I do this pattern on the query Matt's hat, we can get back the group that is unknown to us that's surrounded by these parentheses, so we capture those letters there, and so we return back ATT apostrophe S space H because that was the stuff that was inside the parentheses. Okay? Okay. We'll see a demo of this all in a bit. I know it's a lot of rules, but hang in there. This is the last slide. So the last slide, this is how you do regex in Java. So basically, what you can do is you can make a pattern object. So the problem with Java is like everything is object-oriented. So you need to make like this pattern object and this matcher object to use it in Java. That's just the spirit of Java. So if you use this in Python, it will be a little cleaner. But anyways, in Java, you'll make a pattern and you'll compile that. So pattern is just a string. It was all the blue patterns that I was showing you before. So if you put that in a string and then you throw it into pattern.compile, you'll have a pattern object. And then you can make a matcher by calling dot matcher on the pattern that you had before with the query string that you're going to check against. And that's how you set up your objects. So once you set them up, then you can call a couple of functions on the matcher. So you can do m.find, which is the second thing we were showing you, right? Like, is is the query, can you find the query, can you find the pattern in a substring of the query, right? So that's what the find does. Can you find, oh my gosh, it's so confusing. Can you find a substring of the, can you find the pattern in the substring of the query, right? So can you find a smaller version of, oh my gosh, I keep saying it right. Okay, so can you find the pattern inside of the query string, and there can be extra stuff, right? Okay, so that's m.find. M.group allows you to get back the capturing group that you were looking for. So you can use multiple parentheses and capture multiple things in one pattern, and you can return them according to like the index. But note that we're indexing from 1. So if you want the first one, you use the index 1. If you want the second one, you use the index 2. So we're not zero indexing like we usually do in Java. And then the last thing is you can do m.matches, and that will do the full match. So does the pattern fully match the query with no extra stuff? That's what m.matches does. Okay. All right. So let's do a little demo of why we would ever want to do something like this. Okay. So where is my stuff? This way. This way. One more. Okay. So here's some code. It's posted on the Piazza post. You can download it. It's called regex demo. So inside of this demo source file, we have a function that's given to you already. And I got this from Stack Overflow, so I cited my sources. Okay. So basically what this does is it accepts a string URL. So if I pass in a web link into this function as a string, then what it's going to do is it's going to open up a scanner, right? And if you poked around the projects like Enigma or Gitlet, you might see something like a scanner. A scanner just allows you to read from a file, right? So in this case, we're reading from an online web page. Okay? So the scanner is going to use a delimiter. So what is a delimiter? A delimiter is something that separates a big body of text, right? So if you ever heard of like a CSV file, that stands for comma separated values, right? So in that case, those files are delimited by commas, right? So here we're using \\a. So this is actually a regex expression. I didn't show it to you on the slide, but \a just basically means match the beginning of the entire string, and it's like slightly different than this other thing, which is like a caret, which I didn't tell you about either. But it's okay. You don't need to know \\a. That's fine. But basically, what we do is the scanner works just like an iterator of strings, right? Or it implements it so we can use it in the same way. So we can check if the scanner has a next, and if the scanner has a next, then we can just return that string. So basically, we're asking the scanner to return the thing that it's reading to us. And then this is just a failure case. If there was nothing in there, like if the iterator had nothing to iterate over, we'll just return an empty string just in case something went wrong. Okay. So you don't need to understand that too much, but I think you have like a vague idea of how this works, right? So we'll be using this helper function. So basically, I have an empty main method here, and what I can do is I can use this handy-dandy function, which, what does it do again? It takes a URL, and it returns back the page contents, right? So I can use this function to scrape things off of the internet, and I can download them, and I can make cool products out of them, or whatever I want to do, right? So, for example, if you go to youtube.com, right, you can search for something in the search bar. So what I decided to search for today is this movie I'm really, really excited about. It's called Farewell. How many of you guys have seen this movie? Nobody. It's a very low-key movie, but it's kind of like Crazy Rich Asians. It's like Asian representation in the movie theater, so that's like really big for me because that didn't happen when we were like little kids, but it's happening now. So I think that's really cool. But anyways, this is what we're going to search with today. And if you look in the URL up here, YouTube makes it really simple for us to figure out what we want to search. Like if I want to change my search, I can like change it here, but I can also just change it here because it says search query equals what I just typed in, right? So this is very nice because I can just change the URL and I can change my search query, right? And this is just a page which, because we're computer programmers, we know that this isn't magic. It's just a bunch of code behind it as well, right? So I can use that function and this URL to download the source code for any query I want on YouTube. Okay, so let's just use this as an example. So Let's go back to my code. Okay, so what am I doing? So let's use the function that we had up here. So this is called read URL. So read URL, and I'm going to paste in the URL that I just had. Why is this red? Cannot resolve method. Oh, I spelled it wrong. It's capital URL. Okay. Boom, read URL. It says unhandled exception, Java I/O exception. And that's because this thing here throws an I/O exception, right? So because it uses a scanner, it's going to try to do file I/O. It's going to try to do input-output. And so it could potentially fail, which is why it's throwing this exception. So what I have to do is I need to surround it with a try except statement, right? And I can ask IntelliJ to do this for me by hitting Option Enter. And I can say surround with try catch. Okay? So you get something like this. Okay? All right. So calling the read URL function, we just said returns a string that is full of the source code, right? So let's hold on to that. So we can say that string HTML equals the result of read URL. And we also just found out that I can change this last word here to be whatever query I want. So let me just extract this instead and add this to a query. Or maybe let's just call it search term instead. Okay, so search term isn't defined yet, so I need to define it here. So I'll just have it this, but like if I had a list of movies or something, I could plug that in and write a for loop or something, right? So you could easily extend this to something else. Okay, so great. Now I have string HTML. Let's print out and see what this looks like. Okay. So what do we have? Okay. So this looks like web code to me. This is like a bunch of HTML and maybe JavaScript and other stuff. So let's take a peek at what this is. So I'm going to copy all of this and okay. I'm going to make a temporary HTML file and I'm going to edit that file. And I'm going to paste in everything I just copied. I'm slowly breaking Jackson's computer. Uh-oh. I didn't know it was this long. Oh, okay, finished. Okay, so now, if you remember how to use Vim, I can hit escape:WQ to write and quit this file. Okay, so now I have saved all of that code into temp.html, and this is a web page, so I can just open it. Open temp.html. Aha, this is what it looks like. I'm missing a bunch of like styling and pictures that were on the official YouTube site, but this is basically what was there before. And we have much of the same content. We have like the image that was on the real search page, and we have the title and some other information as well. So in this example, what if we just want to like extract the names of each of the videos that show up in that search results page, right? So in this case, I want to extract like this line of text and the line of text after it. Well, oh my gosh, okay, go back. Okay, so how do I do that? Well, if you've ever played around with like web pages before, you can do this thing where you, oh, what? Okay, wait, oh, I know, okay. You can do inspect in Google Chrome. And you can pull up like this thing where you can hover over stuff and you can see where it aligns to in the code. So here I want to target like the title. And we can see over here that it is referring to code that looks like this. So basically, where is the title in this code? Do you guys see it? I know it's a little small, but I don't know if I can make it bigger. I think it's right here, right? It says title equals the farewell, blah, 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 right? So if I can target that specific piece of text inside my entire HTML file, using regular expressions, I can extract all of the titles of all the videos, right? Okay, so let me try to do title equals quotation mark something end quotation mark. Okay, so, okay. Okay, so instead of printing this, let's do, okay, well, first of all, I need all of that stuff that was on the last slide, right? Okay, Uh-oh, there's a lot of slides. Is it here? Yes. Okay, so copy this. Okay, so my pattern is what and my query is what. Okay, so my query is this HTML stuff that I had, right? Oh, I have caps lock. Okay, and then my pattern is the thing I'm trying to use to match against my query, right? So here I want title equals quotation mark something quotation mark, right? And it could be anything inside of there, so I can use a dot star, right? Okay. So a couple problems. First of all, I need to pass in a string into my compile function, but I also want to use quotation marks in my pattern, right? So how do I deal with that? Escape. Okay. Escape. Escape. All right. Good. All right. So let's run this and see what happens. Oh wait, I didn't print anything, so nothing's gonna happen. Let's print m dot find m dot group one. So this will try to find the pattern inside of the query, and then it will print out whatever is at group one, which is the first thing that is captured. Oh, but I didn't capture anything. Okay, so I need to capture something. So I'm interested in the title, so that's the stuff here, right? So let's capture this. Okay. Now what do we get? Okay, so here I get YouTube video search. What? That is not a name of one of the movies. Where is that? YouTube video. Can I search here? Oh, here. Oh, shoot. There's like other things also marked as title equals something, not just the videos. So I think we need to be a little more clever and not click on random stuff. Okay, so let's try to target one of the video titles again. So if we go here, what else can we use? Oh, maybe only video titles start with href equals quotation mark / watch. So maybe if we do that, we can capture all of the video titles. Okay, so let's make this a little more complicated. Let's say that it needs to start with that stuff, quotation mark / watch, and then dot star. Okay, I have another quotation mark here, so I need to escape it again, right? So this will say that anything that starts with ahref quotation mark / watch followed by anything. Oh, okay, wait. Followed by anything, and then followed by title equals something, will be what I want to target. Right? So let's see what happens now. So what is happening now? I'm getting more stuff. Does anyone know what the problem is? Yes, yes, ding, 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 right? So this is greedy by default. So it's capturing like as much stuff as it can, right? So maybe if we make this reluctant and this reluctant, what happens? Aha! Does anyone see that? I got it. I feel like I'm mining for Bitcoin here. It's like, you know, I'm trying to carefully target stuff. This is kind of what data science is like. So if this is your major, then this is fun, isn't it? I like it. Okay, cool. And guess what? So this is how I extracted the first video name. What if I want all of them? Well, very easy, right? All I do is I can set up a while loop. So while I can find stuff, then I can do m.group1. And so the way the group function works is that it returns back the thing that it just found. So m.find is going to find a different thing, and it's going to keep moving along, kind of like how an iterator does. It's going to keep moving along, and group is going to return the thing that it just matched to. All right, so if I don't highlight everything and I print this, then aha, there you go. So I get a list of all of the movie titles that was in that search result. So you can kind of imagine like all the creative things you can do with this, but this is just like hopefully like to inspire you a little bit. Like the stuff you learned in this class is not useless. Like you can do some pretty cool stuff with this stuff. This stuff with this stuff. Okay, well that's it for today. We'll see you guys next week for our last lecture. Did it not record?